Hi class, welcome. Today we're going to start Unit S, Simple Linear Regression, page S1, and it's on page 149 of your manual. Now this is actually just an extension really of Unit C. Unit C was talking about correlation, the correlation between two interval scale variables. And of course that they are matched. So for instance, we've got the height and the weight of a person. And every person has a height, every person has a weight. And when we take a look at several different respondents and so on, we can come up with a measure of the correlation or the measure of the linear relationship between those two. Same with age and push-ups. We took a look at that, and everybody has an age, and everybody can do a number of push-ups if they tried, and so we could come up with a measure for both of those, and then come up with a measure, the R, which is a measure of the strength of the linear relationship between those two variables. But in this next step here, what we want to take a look at is, well, how do we describe that relationship? Now, if it's a linear relationship, we can describe it as a line with an intercept and a slope. So we would say then that the age of a person then, which will be our x variable then, describes the y, which is the number of push-ups. Push-ups is equal to some intercept plus some slope times age. And we could do the same with height and weight, where weight is equal to some intercept plus some slope times a person's height. So that's describing the relationship as a linear function, and the R is talking about the strength of that relationship. So in Unit S here, we're going to be taking a look at the following. Let me just pull this down a bit here. We're going to be taking a look at the simple linear regression model, and then we'll be doing hypothesis tests and confidence intervals for the slope and the intercept. We'll look at a really important measure called the R-squared measure and the F test that goes with it, and that will be really important when we get into multiple linear regression. And then we'll be talking about, just briefly, using the model for estimating and forecasting. So let's jump in here to page S2, page 150, and we're going to talk about the population regression model. So again, in regression, we're looking at the linear relationship between two variables, an x and a y. Remember that when we say we have one y variable and one x variable, it's, if you think back to Excel, it's two columns. So we have maybe y represents then the weight of people, and then we've got x represents the height of people, and then for every person you've got a height and you've got a weight. So you might have 100 observations or something in both the y and the x columns. So one variable each, but there's many observations. All right. One that we'll be looking at in Unit M here is what describes or what will explain the price of a house. And so y then will be the price of the house. And what we'll find actually is that the size of the house in square feet or square meters, whatever, is actually the greatest determinant in describing the price of the house. It's the strongest variable. And we'll look at how we can look at several x variables together in describing the price of a house here. Now, let's just take a look here at the relationship between price and size. And we're going to draw just a real little diagram right here, like so. So let's see if I'm in the right place. No, actually, I'm going to draw that further on down the page where I got a little bit more room. Here we go. Yeah, there's more room right there. Okay, so let's draw a real simple graph that looks like this. So we're going to have x is going to be equal to the size of the house, and then y is going to be equal to the price of the house, like so. And this is what we would find, is that if we took a look at, let's say, 1,000 square foot houses, so fairly small houses, this is what we would end up with, is that there would be a bunch of houses in the 1,000 square foot range here. Now, the question is, why do they differ in price? Why are some 1,000 square foot houses more costly or priced higher than others? Well, it's because of other factors that we don't include in the model. So, for instance, the age of the house, where it's located, the what number of bedrooms, the number of bathrooms, number of garage stalls, how close they are to schools or supermarkets and things like that. So all those other things that we actually could quantify and we could include, which we will do in a multiple linear regression model. But we're just going to take a look here at the two variables, price and size. So now let's jump over to, say, a 1,500 square foot house. And what we would find here is that we'd still have a spread of house prices for 1,500 square foot houses, but they would be higher in average than would the 1,000 square foot. And then we could do the same for 2,000 square foot houses, and we would end up with, they would be higher as well. So what we would have is a general upward trend, which is what we would expect. As the size of the house increases, so would the price of the house. Now, what we could do is we could find the mean for each of these. So why does it always do this on this page? So here's the mean, here's the mean, here's the mean. And what we're going to do is we're going to draw a line between them. So that's actually the means, and another name for the mean is the expected value of y. What is the expected or average house price as a function here of the size? And what we would find is that we would have an intercept, which we're going to call beta naught, right? We always use Greek letters when we're talking about populations. And then this is going to be the slope, beta 1. So here's the regression line right here. And so we're saying, the way that we read that then is the average house price for a given x. Here's the more formal way of doing it up here. So the expected house price or average house price given a particular x value is equal to some intercept times some slope times the x values. And so this is the equation for the population regression line. Now, for a particular house, though, its actual price may differ from the average price for that size of house. So an average 1,500 square foot house might go for, I don't know, $400,000 in today's market or something. But if you have a price which is, a house which is, say, $480,000, then we say that there is an error term, an error. And it means that we just didn't measure that particular difference here. So this is what the thing would look like. And I've got a little more space down here that I'm going to draw this. So let's draw then the same thing as we had above here, where we have the size of the house, and then we've got the price of the house. And we have this general line that looks like this. Yeah, I know. So we've got a general line that looks like this. And that would have an intercept, and that would have a slope. And that would be the expected y values is equal to an intercept plus beta. So b naught plus beta 1, the slope, times the x values. But a particular house might be, say, here. And if you take a look at it, it's actually higher. We'll call this xi, so the ith house. And it has a price, we'll call that yi. So the ith house, maybe the 10th house in our list, has a price which is actually higher than the average for that particular size. Maybe that size here is, say, 1,500 square feet or something like that. This distance here we call epsilon I. Epsilon is error, and it just means stuff left over that we didn't account for, other factors that were not measured in the model. And so we have something that looks like this. So a particular yi, maybe this would be the better one up here to take a look at. The ith house has a specific price, has a specific size and a specific price, and it can be shown by the regression line, and then the epsilon I, which is the error, is that difference between it and the regression line right here. So that's something that we call the population regression model right there. That differs then from the regression line, which is just all the points on this red line here. So the actual houses then differ according to the model here by the error terms, the individual error terms. And of course there would be a whole column of error terms if you were to do a calculation there, an error for each pairing of houses. Some of the errors might be 0, but some will be positive if you have a house price which is higher than the average for that size, and some will be negative, which if they're lower. So let's take a class example here. Suppose the population regression line is given by the following equation. The expected value of y, which is going to be the price of the house, is equal to 75,000 plus 250x, where x represents the size of the house. A, what is the error term for a 1,500 square foot house that is priced at $450,000? Now, I'm going to assume that you can pause this recording and you can work that out, so I'm just going to continue on through as if you've given that a try. But this is what we would have here then, is we'd have the expected value of y is equal to 75,000 plus 250 times 1,500. And that actually turns out to be equal to 450,000. So in our particular case then, we would say that the actual y value, which is 450,000, is equal to 75,000 plus 250 times 1,500 plus 0. So the error in this particular case then is equal to 0. So we would expect then that a 1,500 square foot house would go for $450,000. I think I said 400,000 before, but I was just guessing. So if you have an individual house now that, say, goes for 500,000, so if y was equal to 500,000, then your error, of course, would be equal to positive 50,000. Seem to have lost that. Come on, I want to get one more 0 in there. There we go. All right. And if it was 400,000, then of course it would be minus 50,000. All right, let's take a look at the interpretation of the regression line. What does the 250 mean? Well, it's the price per square foot. And so what that means then is that every square foot you add to the size of the house will increase the price by $250. So $250 per square foot. When you are building a house, the builder will give you a quote for the price per square foot. What does the $75,000 mean? And this one's kind of a tricky one. This actually is, this one fools people, and you usually get the wrong answer on this particular one here. Most people think, well, it's the size of a 0 square foot house, So that must be the lot price. And it's a good guess, but it doesn't actually work that way. Let me show you how regression works here. I'm going to draw a little picture and say here's the size of the house. Whoops, there we go. Keeps doing that. All right, here's the size of the house. Here's the price of the house. And then here's our regression line that goes like that. The thing that's really important to remember is that regression is good within a certain range. So what's the smallest practical house size that you would expect? It's probably somewhere around, say, 800 square feet or something, and the biggest might be something like 4,000. So regression is good within this particular range. Now, you can forecast outside of that, but you're not going to take your regression line way out here and look at, say, a 50,000 square foot house. That's a totally different animal. And same down here is you're not going to be taking a look at a 200 square foot house, because that's just really a shed, or, of course, some people are into these what do they call them? You know, the little houses, the tiny houses. And so that's a little different. It's a different animal. So this 75,000 actually is just an anchor point for the regression line. What you really want to do is to figure out the smallest practical house size. What is that particular price? And so, you know, it might be something like $150,000 or something like that. I don't know. And then it goes up by $250 per square foot. That's how you interpret that. All right. We're going to go just a little further here. I know this is going to be a long lesson, but I do want to talk about the sample regression model. So this is on page S4. And the problem, of course, is that we don't have access to the whole population. And so you really can't come up with your beta naught and your beta 1 unless you were to take a look at every house in Red Deer or whatever your population is. So usually what we do, of course, is we take a sample. And what we're going to do then is to come up with a sample regression model and a sample regression line. And the sample regression line is given by this equation right here. Now, these y's then are called y-hats. Statisticians are a practical bunch. Or the fitted values. So these are the values, those are the expected house prices given the sample sizes, okay? So the size of the house, we've got the sizes of the house, we've got the prices of the house. We can come up with a sample regression line, which is our best estimate of the population regression line. And the points on the line are called the y-hat values. Now, notice that we have, instead of beta naught and beta 1, we've got B naught and B1. Now, that subscript 0 is, don't confuse that with the naught that we usually put in when we're referring to the value in the hypothesis. So we talk about mu naught and P naught and things like that. That's different. B naught means the slope, the intercept of the sample regression line, and B1 is the slope. Now, how do you get those? Well, let's take a look. Let's draw a couple more pictures, actually, first. What page am I on here? So I'm taking a look at the sample regression line here. And so we're going to have something that looks like this. Let's draw out a relationship between x and y. And this isn't taking a look then at all possible houses, just our sample. Something might be a sample of 100 or something like that. And what we would end up with then is a bunch of x's, and they might look like this, paired with their y's, right? So these little points here then are a pairing of an x with a y. And from there then we can draw a sample regression line. I don't think I hit those points quite right. There would be an intercept. There would be a slope. And this would be the points on the line are the y hats, or the fitted values, is equal to b0 plus b1 x. All right? But, and this is just continuing on with what we had before, for any given house, let's take a look at that picture again. So here's x and here's y, and here's your regression line here, sample regression line. So here are the y hat values. Any particular value, let's say this particular house here, will differ from the regression line by some error term. And we'll call that EI, not epsilon I, because we're talking about a sample now. And so what we have down here then is that for a specific house, you would have this relationship. A specific house, of course, has an x, has a y, and it's equal to the regression line plus some error term. So in this particular case, the error would be positive. And so the sample regression model is given by this relationship. And of course, every pairing of x and y's in the sample have an E, an error, whatever is left over, or how much it differs from the regression line. It could be 0 if it's right on the line, or it could be positive in this case, or it could be negative if it's below the line. All right, in the next part here, we're going to be taking a look at calculating B0 and B1, and I'm going to save that for the next lesson.